minus 5y prime. Y prime is just y2. Plus 3y double prime, that's y3. Okay. Now if I push that minus through, or the 1/2 through there, if we push that 1/2 through there, I'm going to have, oh, and I'm going to move that term to the back. I have 3y1 minus 5/2 y2 plus 3/2 y3. Okay. Oh, yeah, plus sine 5t. Don't want to forget about that. So this is the, non-homogeneous. You can tell it's non-homogeneous because I got this term that seems out of place that involves this t in it, whereas everything else is y's in this case. Okay. Now, what this does is it defines a system, right? So let me start with, and I'm going to define it. I'm going to write the primes on the left side. So we have y1 prime equals y2. It's going to look funny. I'm going to leave a little space there for a second. y2 prime equals y3. Leave a little space. I'm going to put it right there. And y3 prime equals 3y1 minus 5/2 y2 plus 3/2 y3 plus sine 5t. All right. So that looks like a strange form to write with all these spaces, right? Okay. Some of you might see where we're going to be eventually going, because these are going to be the slots that I put them in when we put it into a matrix. Okay? So I want to line up my, these are going to be the whatever they are, variables. Okay? So the reason I wrote it this way is that it makes it easier to put it into a matrix form. Okay. And we will be doing more of that in 5.1. Yeah.
This can be done for any non-homogeneous.
For any non-homogeneous, yeah, but you might not get, this one has constant coefficients, you might notice. If it's not, oh wait, any non-homogeneous? No. So if it doesn't have constant coefficients, these things might be functions of t as opposed to just this entry. Yeah. So these may be functions as well. See, could have a matrix of functions. All right. Okay, so that's one thing that you could do, and that's sort of just resolving an nth order differential equation into a system. And notice we had a third order differential equation. We resolved it into a system of three differential equations. Our unknowns, y1, y2, y3. All right. So another thing that we could do, this is, like I said, this is just sort of preliminary stuff before we move on to chapter 5. But we can solve some systems without using matrices and things like that. Okay. So just like the first time, when you solve a system of two linear equations and two unknowns, a and b or something, or c1, c2. You could use a series of substitutions, right? If I can solve one of those equations for some quantity, I could substitute its equivalent into the other equation wherever I see it, right? So we can do a series of substitutions, and sometimes we may be able to do that with systems of differential equations too, okay? So So solving a system, first order. And yeah, we're going to use substitution. All right. So say the system is as follows: x prime equals negative y, simple equation. Y prime equals 10x minus 7y. Okay. So just for reference, I'm going to call these equations 1 and 2. Oh, and say we have an initial condition, say with x of 0 being 2, y of 0 equaling negative 7. All right. Any ideas? So the bottom equation involves x and y as well as y prime. The top equation just involves y. But the thing about it with this way is, yeah, you can sort of, I don't want to use the word fumble your way through it, right? Looking for substitutions that you can make, but the book calls it an ad hoc way. Just find out, manipulate it until you see something you can sub into the other equation until you get something you can solve.
Could you take like for instance, could you use like implicit differentiation to like on the x prime is equal to negative y prime to find out what
With respect to t, right? That's one thing I should mention.
So
So
what's your parameter here?
x and y are the independent variables. Obviously, they got the primes on them. So primes.
It's harder, yeah, to know if you can do implicit without Leibniz notation or differentiation.
So primes represent derivative with respect to t in here. So that's our independent variable of both of those functions will be t. So we are looking for two functions, x of t, y of t.
Yeah, so then could you do on the first one separable, right? And then you could have y prime and then sub it into the other one with x. And then you also have y, so you could, I don't know if that works, but that's what I would try to do.
Right. Yeah, you could certainly differentiate both sides because they share the same independent variable. So if I differentiate with respect to t, you can do it to both sides.
Sure.
Right. So yeah, we could differentiate one. And that would give, so x prime prime, that's x double prime, right? Equals, so derivative with respect to t of x prime is just x double prime. Derivative with respect to t of y, y prime. And the negative is a constant, it's negative 1. So constants come through the differentiation, sometimes called a differential operator, right? Constants come through that. And I could solve this for y prime. So y prime equals negative x double prime. So I could sub that into the other equation. So every time I see y prime, oh, I can put negative x double prime.
So you can also sub the negative x too.
Where at? What
The negative y for where it says negative 7y.
Oh, right.
Sub that to,
7y.
and then
Y
you sub
is
that.
also equal to negative x.
And
Right.
your second order or whatever.
So I could write this as 10x minus 7 and replace y with negative x prime. Oh, now we got an equation that involves x's and their its derivatives. Okay. So one more step here, clean this up. This becomes 10x plus 7x prime. Getting all this onto one side of the equation, I would have what? Let's keep the 0 on the left. Add x double prime to both sides, so I'd have 0 equals x double prime plus 7x prime plus 10x. Good. And this is homogeneous.
You don't have to do that one.
Yeah. Yeah. So on this guy, remember, t is our independent variable, so if we go through our regular routine, assume that x of t has the form e to the rt, we could find its characteristic equation. Okay? Can I squeeze another line onto here? So its characteristic equation would look like, well, x double prime would be r squared e to the rt. So we'd have r squared plus 7r plus 10 equals 0. And lucky for us, is that a factor?
Yep.
Yeah, they're nice with these examples. Okay. So, factor this, what do we get? Plus 5 plus 2. So the solutions would be -5 and -2, right? Distinct real solutions to the characteristic equation. So x of t will be what?
C1 e to the negative 5x, sorry, plus C2 e to the negative 2x.
Mm-hmm.
Oh, yeah.
Oh, yeah. T.
Right, independent, right, I know, it's so hard. I'm not a fan of switching around so much and calling x the dependent variable in all these examples, but it happens. Okay, so that's x of t. Now, what else do we know in this, oh,
We got additional condition.
y, oh, y equals negative x prime. Okay, so from equation 1, we know that y is equal to the opposite of x prime. Okay. So opposite of, let's differentiate. X prime is going to be, at -5 is going to pop out because of the chain rule, so I'll have -5c1 e to the -5t minus 2c2 e to the -2t, right? One moment pushing that negative through, and that puts them all positive again. That's nice. I'm going to have 5c1 e to the -5t plus 2c2 e to the -2t. And that would be y of t. Okay, good. Now what?
So,
Right. We have two functions, and here's the thing: if I wanted to find both C1 and C2, if it was just a single differential equation, right, I would need 2 initial conditions on it to find those, wouldn't I? Right. Same thing with that. But taken together, I have 2 initial conditions, and that should be enough to take care of it. So our initial conditions, first we got x of 0 was 2. Okay, so putting in 0 for 2, we get, I love doing that, I just get C1 plus C2 equals 2. And the other initial condition involves y. Y of 0 was -7. All right. So putting that into our function into our expression for y, what do we get?
-7 is equal to 5c1 plus 2c2.
Right. So e to the 0s, those, yeah, e to the 0 is 1, so I just get 5c1 plus 2c2 equals -7. Okay, good. Now, you know, you can do this by hand. We've seen how to solve that by calculators. There's also websites, right, stuff like that. One thing I want to show you is some of you, and this is just where we're going, if we write this in matrix form, just to give you a little taste of it, the coefficients of C1 and C2 are just 1 in that top equation, right? The equations, the coefficients of this one are 5 and 2. Now, we haven't defined this yet. We're going to get there. But times C1, C2, if this is a column vector, equals 2, -7. Okay? If you've seen multiplication with a matrix and a column vector, it's just the dot product of each row with this column. 1C1 plus 1C2, it gives us that equation back, equals 2. Okay? 5C1 plus 2C2 equals -7. So this is written as a matrix equation. Okay? Don't worry, we're gonna do an intro into matrices and operations and things like that after a break. But you can do this, solve it various ways. Okay? We get, without showing the work, C1 is -11/3. And C2 is 17/3. Okay? Alright. So, our solutions, this is a pair of functions, x of t with these constants. C1 is -11/3. I'm going to write it in reverse. I don't like negatives hanging out front, just me. Alright. So I'm going to write the 17/3 out front. 17/3 e to the -2t minus 11/3 e to the -5t. And then y of t, I'm going to switch them again. So C2 is 17/3. 2 times 17/3, that's 34/3. 34/3 e to the -2t. And C1, -11/3. So 5 times that -11/3 is -55/3. Okay, so we got some nasty fractional coefficients. Okay. All right, a couple things to note. First, there's not really a formal method to go about solving a system like this. Okay, it's if I differentiate this, I notice I can substitute in there and get rid of this thing and get it all in terms of x or something and its derivatives, or all in terms of y and its derivatives, and then solve it. So there's really no formal approach. Okay, just a sort of series of substitutions. It's what the book calls an ad hoc method. Okay, so it gets kind of messy, especially if you have 3 equations, say x prime, y prime, z prime, or something. 3 equations and 3 dependent variables. Okay. So there's no straightforward method. It's just try things until you get an equation you can solve. Now, one other thing I want to note is that taken together, these are functions of a parameter t. Okay, so they have the same independent variable. Taken as a pair of functions, this can be thought of as a, what kind of function is this? A what? Vector function or parametric? Yeah, parametric function. So this yields, you could think of it as a singular parametric curve. Or, I have that in my notes, or vector function. So nailed it. Both. You could think of it as a vector function, vector quantity, in the xy plane. Okay? So both functions of t, x of t is one thing, y of t. For each value of t, this gives you a point in the xy plane. As t varies, this is a moving point in the xy plane given by these, you know, parametric equations. All right, so one thing I want to show you, again, this is like reason number 3 to use, don't look, don't look. This is reason number 3. This is already created, so you don't, these things that I put up, you don't have to do the coding for this, okay? Get rid of that. And I'm going to close up on this part, okay? And I'm not sure how to put some more spaces in here. I got to work on that. But up here, we defined that equation. So differential equation right here, x of t, t. So x of t is the dependent variable, t independent variable. So first equation is x of t equals negative y. So x equals negative y. That was our first equation. Okay. The second equation was it 10x plus 7y? Was it 10x minus 7y? Yeah. Okay. So notice the independent variable has to be put in on both of those. But this is a DE plot, so you got to include DE tools. What this does is it takes those simultaneous equations, system of equations, instead of solving and spitting out the answer, it plots the parametric or vector function x of t, y of t. Okay. Based on these two initial conditions. So initial conditions right here, x of 0 equals 2, and y of 0 equals negative 7. So those were our two initial conditions. And this is what the parametric curve would look like. Think. There we go. So what it does is it creates this thing a lot like, looks like a what? Slope field, direction field. But with one difference. Since this is a parametric thing, and our vector, when we created direction fields for a single differential equation involving y or something like that, it gave us a function, so it was always going left to right unless I got two halves of the function. But here, this is the sort of phase diagram of a parametric curve. So it graphs, and the independent variable is t. If x prime of t is negative, that means x is decreasing. So it could be moving to the left. If x prime of t is positive, that means x is increasing, so x would be moving to the right. And it looks like for most of this, y prime is positive, which means the y value is increasing. Okay? And the initial condition we gave it was x of 0 equals 2. And this is, and by the way, that value in parentheses is t value. We don't see that on here. This is still the xy plane. So for the invisible parameter t, when it's 0, we get the point, well, x coordinate is 2, the y coordinate is negative 7. So right down here, the point 2, negative 7. Okay? We could also change that. Say at time 0, the x coordinate is 5, and the y coordinate is 0. Where is this going to start? Does it start at the point 0, 5?
No.
All right, that's the x coordinate at time 0 is 5. The y coordinate at that same instant is 0. So the y and x value, or the x and the y value, 5 and 0, should start right here. So change that up. This is already pre-programmed. It's just a template. There we go. So there's the phase diagram, including that particular solution curve. Okay. All right. Now let's look at another one. Let's see. Did I erase all of those? That was a good one. Okay. So let's look at this. Let's look at this last one. We're not going to go through solving it. This is the very last one. This one goes to the one above it, but right here. So this DE plot. This is the big plot structure that plots the whole direction field. Inside this plot structure is the definition of the system. So x of t That's the dependent variable, independent variable equals negative y of t. So I'm just going to write down, take from that the system that's in here. So x prime equals negative y. So that started off a lot like the one we had. But over here, differential or derivative, y of t, so that's y prime, equals, and this would be 1.01x minus 0.2y. Yeah. Okay. And it gives an initial condition at when t is 0, x is 0, and y is negative 1. So one thing that you can say is at t equals 0, the point x0, y0 just gives me 0, negative 1. This is what it means by parametric. We're parameterizing it by that variable t. Okay? So that would be my initial condition. It goes from 0, negative 1. And without solving it, without having to solve it, we can see a picture of what's called its direction field or phase portrait. There you go. This one spirals in, so x only goes through two bounds. Dx dt is decreasing till it gets to there, and then increasing. Dx dt is positive, so x is increasing. All right, so it might be some sort of sine and cosine, but the problem is the amplitude in the x direction is getting smaller, like a variable amplitude that's shrinking. Same thing in the y direction. And did it go through that point, 0, negative 1? Right there. And at that instant, its derivative, x prime, y prime, would give you its direction vector, or sorry, the velocity vector, right? At an instant, x prime, y prime tells me how the x is changing at an instant, how the y is changing at an instant, so x prime, y prime would be the velocity vector. It would be pointed that way. And goes right in towards the center.
Our tools for vector calculus.
What's that?
Now we can use all of our tools for vector calculus.
All right. So let's take it. I want you guys to get some practice. Try, just for the sake of time, in number 1, do A. So skip B in class on the front page.
There's one more person.
Oh, okay.
See if you see it.